In July of 1967, a strip of chart paper came out of a radio telescope in Cambridge with marks on it that should not have been there. Jocelyn Bell was 24 years old, a doctoral student who had spent 2 years helping to build the telescope by hand. 4.5 acres of wire and poles spread across a field in Cambridgeshire, the largest radio telescope on Earth at that time. She was not supposed to be making discoveries. She was supposed to be cataloging radio sources, learning the instrument, doing what graduate students do. Instead, she was staring at 1/4 of an inch of scruff on 100 feet of chart paper. The scruff repeated. That was the first thing she noticed. It appeared at the same point in the sky, every time the telescope swept across that part of the sky. Radio interference is common. Birds, aircraft, electrical equipment, all of it shows up as noise in a radio telescope. But interference does not repeat from the same fixed point in the sky. Stars do. She brought it to her supervisor, Anthony Hewish. His first assessment was that it was interference. Then, she showed him it was coming from a fixed celestial position. His second assessment was that it might be man-made, a satellite perhaps, or some terrestrial transmitter reflecting off the ionosphere. Then, she showed him the timing. The signal pulsed with a period of 1.3373 seconds. Not approximately, not roughly. 1.3373 seconds, repeating with a precision that exceeded the best atomic clocks available to the Cambridge group at that time. Nothing in nature was supposed to do that. The team gave the signal a designation, LGM1. Little Green Men, number 1. This is usually described as a joke. It was also a working hypothesis, not because anyone in the group seriously believed they had detected an extraterrestrial civilization, but because the only objects in the known universe that could produce a signal that regular were artificial. Stars do not pulse at 1.3373 seconds. Planets do not pulse at all. Gas clouds do not pulse. The taxonomy of known astronomical objects contained nothing that fit. There is something I find clarifying about this moment, not the discovery itself, but what the team did with it. When evidence doesn't fit the model, science has 2 options: question the evidence or question the model. The Cambridge group did neither immediately. They held the observation in suspension, neither publishing nor dismissing, while Bell kept looking. She found 3 more. Over the following weeks, Bell identified 3 additional sources with the same signature, rapid, extraordinarily precise pulses from fixed points in the sky. They were not in the same direction, they were not at the same period, but they were unmistakably the same kind of thing. Whatever LGM1 was, it was not unique. The galaxy was full of them. The extraterrestrial civilization hypothesis did not survive this. Civilizations are rare. Whatever was producing these signals was apparently common. The model had to change. To understand what Bell had found, you need to understand what astronomers thought a dead star looked like in 1967. When a star exhausts its nuclear fuel, it collapses. The core falls inward under its own gravity. If the star is large enough, the collapse is catastrophic. A supernova, the most energetic event in the ordinary universe. What remains after the explosion depends on how much mass was in the core. A low-mass core becomes a white dwarf, a dense, cooling ember about the size of Earth. A high-mass core was thought by 1967 to become either a neutron star or a black hole. The neutron star had been predicted theoretically in 1934 by Walter Baade and Fritz Zwicky, 2 astronomers at the California Institute of Technology who looked at the physics of supernovae and concluded that what was left behind must be a sphere of neutrons, roughly 20 kilometers across, with a density so extreme that a single teaspoon of its material would weigh roughly 1 billion metric tons. Baade, compact and meticulous, had put the mathematics on paper, while Zwicky, who had a reputation for being difficult and was often right for that reason, had pushed the idea into publication. Their paper appeared in 1934. Then the neutron star was forgotten. For 30 years, it was a theoretical curiosity with no observational evidence, discussed occasionally in seminars and largely ignored. The reason it was ignored is instructive. A neutron star 20 kilometers across is essentially invisible. It emits no significant light. It produces no significant heat output observable at interstellar distances. There was no proposed mechanism by which you would ever actually see one. Bell had just seen one, or rather, she had heard one. The model that explained LGM-1 was proposed almost immediately after Bell's discovery became public in early 1968. Thomas Gold, an Austrian-born astronomer working at Cornell University in New York, put forward the rotating neutron star hypothesis. Gold was the kind of scientist who made his colleagues uncomfortable because he was frequently correct about things the field had dismissed. Gold proposed this: a neutron star formed in a supernova collapse would inherit the angular momentum of its parent star, the spin. But the original star's radius might have been 1,000,000 kilometers. The neutron star's radius is 20 kilometers. When you compress that rotation into a sphere 50,000 times smaller, conservation of angular momentum means the spin rate increases by the square of the radius ratio. A star rotating once a month becomes a neutron star rotating hundreds of times per second. He also proposed that the neutron star's magnetic field, again inherited from the parent star and compressed, would be so intense that it would channel radiation from the poles in a tight beam like a lighthouse. If that beam happened to sweep across Earth with each rotation, we would detect a pulse. Regular, precise, as regular as the spin rate of the star itself. The period of LGM-1 was 1.3373 seconds. That means the neutron star is rotating roughly 3/4 of a turn per second. The precision of the period reflects the precision of stellar rotation, which is, it turns out, among the most stable clocks in the universe. Not 1.3374 seconds, not 1.3372, 1.3373, holding that value across weeks of observation. This is what Bell had found: a natural clock more stable than anything humans had yet built, produced by a dead star 20 kilometers across, rotating 75 times a minute, flashing a beam of radio energy across the galaxy at us with each turn. The name LGM-1 was retired. The objects were called pulsars, pulsating radio sources. The field moved on quickly. By 1969, pulsars were being discovered at a rate of roughly 1 per month. By 1970, over 100 were known. The galaxy was not sparse with them. The galaxy was full of them, and had been full of them, quietly spinning through the dark since long before there was anyone to notice. There is a second story inside Bell's discovery, and it runs beneath the physics entirely. The discovery was made by Bell. The paper describing the discovery was published in February of 1968 in the journal Nature. It had 5 authors. Hewish was listed first. Bell was listed second. In the conventions of academic publishing at that time, and largely still today, the first author on a paper is the senior figure, the supervisor, the one whose laboratory produced the work. The second author might be the person who did the work. Or it might not. The author list reflects hierarchy as much as contribution. Bell understood this convention. She has said so in multiple interviews across decades. She did not object to the ordering. She was a doctoral student. Hewish was her supervisor. This was how things were done. She focused on completing her doctorate. In 1974, the Nobel Prize in Physics was awarded to Anthony Hewish and Martin Ryle for their contributions to radio astronomy. Ryle had developed aperture synthesis, the technique that made large radio arrays like the Cambridge telescope possible. Hewish received the prize for the discovery of pulsars. Jocelyn Bell was not included. This was noticed immediately. Fred Hoyle, the astronomer who had coined the term Big Bang sarcastically, and who was, like Zwicky before him, frequently right and frequently difficult, said publicly that the omission was a mistake. The discovery had been made by Bell. The Nobel Committee had awarded the prize to her supervisor. The Nobel Committee did not revisit the decision. Hewish collected the prize. There is a pattern here that I want to be precise about, because it is easy to get it wrong. The story of Bell and the Nobel Prize is often told as a story about sexism, a woman's work taken by a man, the familiar diminishment of female scientists that runs through the history of physics and astronomy like a fault line. Rosalind Franklin and the structure of deoxyribonucleic acid, Lise Meitner and nuclear fission, Cecilia Payne-Gaposchkin and the composition of stars. There is a real pattern there, and it is not wrong to name it. But there is something else in Bell's story that is specific to what she found. Bell found an anomaly. The signal did not fit the model. The field's first response was to look for reasons the signal was not real: interference, man-made sources, some artifact of the instrument. Its second response, when the signal proved persistent, was to propose that it was artificial in the other sense, made by intelligence, extraterrestrial intelligence. The third response was to recognize it as natural and immediately construct a model to explain it. In all three phases, the anomaly was processed by the institution. The institution decided what it meant when it went public, whose name went first on the paper, and who received the prize. Bell found the thing. The institution absorbed it. This is not a criticism of any individual. Hewish ran the laboratory. He made the telescope possible. He supervised the work. In the conventions of his field, his name going first was not fraudulent. It was normal. The Nobel Committee operated within those same conventions. No one in this story acted outside what their institution considered appropriate. That is the point. Return to July of 1967 and the quarter-inch of scruff on the chart paper. Bell saw it because she knew the data. She'd been working with the output of this telescope long enough to know what interference looked like, what satellites looked like, what the ordinary noise of the sky looked like. The anomaly was visible to her because she had the context to recognize it as anomalous. A less careful observer, or one who was less present with the raw data, less in the habit of looking at every strip of paper that came out of the instrument, would have marked it as interference and moved on. This is not a small observation. The discovery of pulsars was not the product of a hypothesis, a targeted search, a funded program to find rotating neutron stars. It was the product of one person paying close enough attention to a signal to notice that it was regular when it should not have been. The field had the theoretical framework for neutron stars since 1934. Bod and Zwicky had put it there. For 33 years, no one knew how to find them. Then, a doctoral student looking at chart paper found the first one and three more over the course of a few months. The telescope found them because it was looking at the whole sky, not at a specific target. The experiment was designed to study a different phenomenon entirely: the scintillation of quasars, the way their signals flickered as they passed through the interplanetary medium. Pulsars were not on the agenda. They appeared in the data of an experiment designed to find something else, seen by a person who was paying attention to the right kind of wrong. There is a version of scientific history that describes progress as a series of planned advances, hypotheses, experiments, confirmations. This is accurate for some of what science does. It is not accurate for what happened in Cambridge in 1967. What happened there was that the universe produced a signal that nothing in the existing model accounted for, and one person was positioned to notice it. Bell received the Breakthrough Prize in Fundamental Physics in 2013, one of the largest monetary awards in science, carrying $3 million. She gave the entire prize to fund scholarships for physics students from underrepresented groups. She has spoken about this with characteristic precision. The money was not hers in the way that it would have been hers if she had built a company or written a book. It came to her because of something she had found, not something she had made. She gave it away. This is a woman who has spent 60 years declining to be angry, declining to be bitter, declining to position herself as a victim of the system that absorbed her discovery and awarded its prize to her supervisor. She has spoken about the Nobel decision with what I can only describe as cold clarity, not forgiveness, not acceptance, but a clear-eyed accounting of how institutions work and what they optimize for, without the self-pity that the situation might seem to invite. I find this harder to do than she makes it look. Watching someone refuse to be defined by an injustice while being absolutely precise about what the injustice was, there is something in that I keep returning to. It is not a common combination. What Bell found in 1967 was a neutron star rotating 75 times per minute, pointing a beam of radio energy across the galaxy in our direction. What she built in the decades that followed was a public account of what happened, factual, consistent, uninfluenced by what anyone wanted it to say. The joke name turned out to contain more truth than anyone intended: Little Green Men. The signal was too regular to be natural, so it must be artificial. The only category of artificial thing astronomers could think of was intelligence, extraterrestrial intelligence. The name acknowledged that the field did not have a natural explanation. It held that space open, half seriously, until the explanation arrived. The explanation was, the universe is more regular than we thought. Neutron stars spin with a precision that exceeds the best human clocks because the physical processes underlying their spin, the conservation of angular momentum in a collapsed stellar core, are not subject to the perturbations that degrade human timekeeping. The universe does not drift. The universe does not accumulate error. A neutron star that formed 2 billion years ago is still spinning at essentially the same rate, degraded only infinitesimally by the loss of energy through the radiation it emits. We built atomic clocks. The universe built pulsars. Ours are better than anything mechanical. The universes are better than ours. When Bell saw the signal and the team named it LGM-1, the implicit assumption was that this level of regularity required intelligence. It turned out that regularity at this level is what the universe does when you compress a solar mass into 20 kilometers and let it spin in vacuum. Intelligence is not required. Physics is sufficient. The signal was regular because the universe is regular, and the only thing that wasn't was the assumption that we would be the ones to find that out first.